In American, it's called Tic-Tac-Toe. In British English, it's called Noughts and Crosses. In Polish, it's Kółko i Krzyżyk. Players take turns and try to, you probably know how it works, but the players play in turns. And I have to, can you test if it works? I can put a move, and the computer has computed its move. And it works. Okay. So I will introduce you to the game a bit, and then we'll see how, because it already works. The computer can solve it, so there is a Minimax algorithm somewhere here that solves the problem. And the goal would be to check if we can generalize the algorithm so that it works for any game, like bigger, noughts and crosses, drafts, chess, or whatever we can think. So first, let me introduce you a bit to a game. This is how, and tell me if I'm going too fast or too slow, so I can correct myself here, because I cannot imagine what you are feeling right now. So here is a structure that represents the entire state of the game. There is a board. It will be like, rather than typing the three directly, I can control the size of the board. Right now it's 3 by 3. So this is an array that stores 9, is capable of storing 9 symbols. Each symbol is either empty, or it has a knot, or it has a cross. And, which is even more important, we have a two-state data saying which player's turn it is. We start from knots doing the first move. So there's one enumeration for the symbols we use. The other is, here is the player, which one currently moves, and we'll see it later. At each time, there is 4 major states in the game, like not finished yet, or finished and it's a draw, or finished it and it not win, or it's finished and crosses win. There is a function which is quite long. You don't have to really think of it to display this board to the screen. And there is the algorithm that checks whether the according to the current state of the game, it's finished. So basically, what we do here, we check first for, we have to look at it from the end. We check if knots win, that is, if there is a row or a column or a diagonal where knots have occupy all 3 places. If yes, we say that the knots win. Then we check the same for the crosses. If there is a row, column, or diagonal occupied by the crosses, they win. Otherwise, we check if there are still empty fields. If there is any empty fields, the game is not over yet, at least now. Otherwise, if all the fields are occupied and no the players wins, it's the draw. Here is our main function. We create the state of the game. We print the board which is empty at the beginning, and then by default, the first move is performed by the human. So there is a function that takes input from the human. We first have a precondition that the game is not finished yet, because otherwise it doesn't make sense. We get the string and check if it's of the form like A1 or B2. I think it's here. So we parse some strings to see whether it is the right, if it's the right format. If it is the right format, we get our move. We just check if this move is, I don't think we check whether it's applicable or not. That's beside the point. The point is, at the end of this function, we get a move. Move is represented by the integer. It's an index of the field where the next symbol will be put in. Whether it's noughts or crosses depends on the state of the game. So once this is done, we apply the move. So at the position indicated by the user, we put the right symbol, we flip the player, now it's the other player's turn, and then, well, then we check if the game is not finished, because it may be finished, because we are in the loop, and then the computer does the move. We call this function solve, which is all the fun in this game. It gives us a move, and again, we apply it to the board, check if it's finished. If it's finished, we break the loop. Otherwise, we do the next round. So all the fun. Do I hear a question? Someone turned on the mic.
Sorry, Andrei. Can you stop for a while and check, because I think that there might be some people that tries to join the meeting.
Yeah.
So unfortunately, you have to accept them. Yeah, so.
Thanks.
Okay. Thanks.
Okay, I'm still accepting. Wow, it's like many people are. Okay. So whoever joined now, we are just about to see the most attractive part, which is the solve function. It's in a separate file. Here is our Minimax algorithm. This is unimportant. Okay. At some point, we iterate over all the field, over all fields we have in the board. Someone is joining. Over the empty ones, we filter the empty ones, and if it's empty, we try to score it. So we copy the state of the game, and on this copy, we apply this move that we have here. We try to see what happens if we put a nought or cross in there. Nought or cross, depending on whose turn it is. Once we have applied the move, we score it. So here we are keeping the running score of the best move found so far. We try to look for the biggest score over all the possible moves, and we return it. Actually, we return it per a move and its score. And now the question is how we score the game. And the way it works is we run the function recursively. First, we check if the game isn't finished, because it's possible that after this move, the game has finished. So if it's a draw, the score is neutral. If noughts win is oriented toward noughts, we give the maximum possible score. If noughts lose, we get the minimum possible score. And otherwise, we skip the condition for now. This is just to stop the algorithm if it's running for too long a while. And if none of the conditions take place, we solve again. We call the function recursively, but this time on a different state, on the state modified. So we look for the optimum solution for the other player. Now we call the algorithm again. If it's the other player, here we have lambda that computes the better, whether one move is better than the other. If it's the other player here now, it will be crosses. Then we are looking for the minimum. So now it's like we are speculating what the other player will do. Try to maximize our function, our move, and the other player tries to minimize it. So it's her turn or his turn. She tries to minimize it, applies the same algorithm again, but looks for the minimum possible score. And again, the minimum possible score of the other move is to compute the score recursively. And then unless the game finishes, we are going back to the first player and he tries to maximize again. So it's the third level of recursion. At the first level, we try to maximize. At the second, we try to minimize. At the third, and there we go down and down, and a couple of things can happen. Either the game finishes, and in case of knots and crosses where it's just 9 fields, we are guaranteed that it will finish in a reasonable time. So at some point, one of these 3 conditions will be applied. Otherwise, if we make the game bigger, it's possible that with our tree that we grow will grow so big that the machine resources of the machine can no longer handle it, and then the program will just hang. So we apply this level. Each time this recursion goes, we decrease the level. So if we go back, we have started with our solve algorithm with some search depth. I think it's 10. Yeah, it's 10 by my default. And each time it is decreased. Let's see where it is decreased. Here. And at some point, when it goes to 0, we apply the static score without the recursion. Static score is a way of looking at the state of the game and trying to assess which player has a better position. Our static score is here, and the way I implemented it is it's difficult to say who wins. So you get a point where when you have occupied the central field. So this is what it says here. If it is even number of rows and columns, there is a central point, and if nodes get the central point, they get 1 point. If they don't have the central field, they get a negative point. And in case it's not odd but even number of rows, sorry, it's 3 by 3, 3 is handled by this case. If we get 4 by 4, there is no single central field, so I'm checking all the 4 central fields, the square in the middle, and check who occupies it, and I sum it, and this is my score. So the score like this is never ideal, but it gives some approximation, and we have an ability to stop the algorithm. So that's about it. I think I have finished describing it. Let me see if somebody has joined, but no, I don't think so. Do you feel like it's explained enough? Do you understand what is going on here? No response. I don't know if you can let an algorithm in 5 minutes like this, but this is what we've got. I was suggested we keep it to 90 minutes, so I have to keep it fairly short. And we can actually play it. puts a cross immediately in the middle. Okay. Okay. Nobody wins knots and crosses, so we know how to play. And the idea here is this algorithm solve should be generic enough to work for any game. And the task for today will be how we separate it from our specific game of knots and crosses. So apparently there will be a concept that will describe the game, and there will be a templated algorithm that will use this concept. And it is a fiction that we can think for an hour or 2 hours and present a good concept. Building a good abstraction is a iterative process. So we will only be able to do one iteration and hope it will work. Because what I'm sharing with you, some 10 years ago, I really wrote the algorithm for solving drafts. But in order to test it, I needed a smaller game like the one here, Knots and Crosses, where I can really debug it and see what's going on. So it's a good approximation to start from some game, maybe two that we have in mind. And at some point, we will learn that our generic algorithm that actually doesn't handle all the possible games there are, and this is fine. We can refine it later on. For the first iteration, it will suffice our game here. So apparently, something like a board is not necessary for a game of two players when they take turns, and at some points one wins. So board is something specific to knots and crosses. Also, the board in general is not enough. If we were solving chess, in chess there are, apart from the board, you have to know the history, what happened before. Like if we had the castling move, a board can look the same, but you can make the castling move if you didn't make it before, if the king wasn't moved before. So there is more to the state than whose turn it is and what board it is. So somehow this has to be abstracted from the algorithm. The algorithm doesn't have to know about the board. Wherever we get the access to the board, this will have to be somehow abstracted away. So we can make an attempt to do it. Maybe we need another file. Game, game or game state. Let's call it game for now. So what do we do in the algorithm? We first make an assumption that that the game is not finished yet. So it's our precondition to our solve function. So we have to be able to say that the game has finished. Finished is implemented, I think, in the game. In order to implement function finish, we have to know the state of the specifics of our game. So it cannot be part of the generic algorithm. It has to be part of the game. The game has to tell us when it's finished or not. And now finish is one of the four states. It's not finished actually, and it's a draw, it's not swing, and crosses. Probably in other games like chess, there is no knots and crosses, so we have to invent a more abstract term, but it will be still four states. It's possible that there is more states where the game ends, but we will not consider them for the first iteration. So there will be something like a let's put it in the names. So in some game, there is a state that tells us it's not the finish, but how the game can finish, or the state in a higher level like this. So not yet finish is okay, draw is okay. We probably need to invent something here like yin and yang. That looks like sufficiently abstract. Sufficiently fair. No game is preferred. So for our game, it should be possible to ask if it's finished or not.
Tam masz literówkę w słowie koncept.
Now, okay, G, we can ask finished problem. And it should return one of the four states. So the result doesn't have to be exactly this type, but it has to be convertible. Now let's see if it still compiles. Actually, I don't know why it compiles, given that I haven't included concepts folder. Header. And let's see. Or let's see here. We'll include the solver. It includes the game and the concept, and we will see if it even works. Integer is not supposed to be a game. game, which is called the game, I think. No, it's called just state. Not an ideal name. Okay. Isn't also okay. Finished. There's no function finished there. Looks like the bridge. Finished. But it returns something else. So we will have to adapt it a bit. So that it returns our enumeration. Now it will be okay, finished. Or let's do it this way. Now it's using a bit different names, so the program will not compile for other reasons. Too much. Okay, has not been declared. Okay, we have to rearrange the headers. So there is a couple of things here. It's not okay. Where does it start? Finish has not been declared in game. Is it so? Finished. According to my understanding. Yeah, it's finished. Yeah, so there is no nots anymore. It's yin and yang. No. And in solver, I want it nots. Yeah, so now our game is a concept, although the concept itself is degenerate. But this is just a test. We make the, oh, everything now compiles, so it's quite reasonable. I think we can already make it a template. But it's not the function that I'm most interested in. But okay. Here's some function. can already constrain it with our concept. Yeah, and look what happens. We have our function itself is already a template, and it's constrained by a concept. And of course, our concept, it uses more than a concept requires, because the concept only has a function finished. And obviously, we need more than that. And we are using more of the interface. And we are forwarding to a function compute score, which is not constrained by this game at all. And it all works because, as we said the last time, the concept constraint like this is only informative of what we will fail if our caller does not provide this. But it doesn't mean we will succeed if he provides. We will fail. If you try to instantiate it with int, we will fail. I guess what I'm trying to say is what we need here in the body, there's no relation to what we expect here. It's just two different things. It's a nice hint we are giving to the user, but it doesn't constrain us or bind us, the implementers of the function, to only use this interface. This is why this works. And this is why the migration from a concrete function to a generic library is so easy, because I do not have to think now whether I'm only using this concept and if I'm not using more. I can put it here as well. I think there's another function here. We can. Okay. So what is more? At some point, what we are doing here is, well, here, it is not that obvious, but what we are doing is we are trying to check every possible move. So there is a notion of every possible move given this state of the game. Here, we are lucky that we know how the game is implemented inside. We know that there is a move wherever there is a field that doesn't have a knot or cross inside. But in a more abstract game, there will be no some things like empty fields, or like in chess, there is empty regions, but it doesn't mean they represent a move. So a move will have to be something more abstract. Our game will have a associated type move. I don't know, maybe we'll call it like this. And once the game is called, and there will be a mutable version of game here, but for now we will not use it. There is something like a move. If we do it, our concept, our game no longer satisfies the concept, so we have to add it. Move in our case is just an int. And it all just works, but for safety reason, maybe even inside our program, we don't want to use int because we have an int that represents the extent of the game. We have an int that represents the score. Now we have an int that represents a possible move. And it's easy that we'll pass the score where the move is expected, or that we pass the dimension where the score is expected. So it's good to make them stronger type types. So maybe it is a good idea to introduce like structure here. It doesn't have to do anything with our generic library, but with good coding standards. Now our game will not compile. Okay, actually it's not. It is nested in the game. Sorry, it's G. So now our game, our nodes and crosses are represent the game, but why compiles? Because we never use it actually. It will become apparent later. We will maybe leave it for now. And this will come back where we try to introduce the notion of possible moves. So we expect that the game, here we iterate or we try to extract from the states possible moves. So we will expect that the game is able to tell us what moves are possible at a given moment. So there will be something like, now in order to keep this short, I will use a vector as an interface, which is not really optimal, but will make us fit into 90 minutes slot. We will expect that there is that function, member function. I don't know why I made it a standalone function. It could have been a member. Maybe I would go with the member stuff. Possible moves. And I expect that it will return a vector of moves. Ideally, in the future revisions, it would not be a vector because the vector allocates memory and it may not be necessary, but it will be something that will allow us to iterate over. Now a vector is good enough. We will iterate over vector. Our game is no longer a, sorry. So unfortunately, we have to repeat. So, okay, now our game is not a game because it doesn't have this function. how do we implement it? It's actually easy. For every we almost implemented it here. For every index. If the corresponding field is empty, it is possible. Not really. For some reason, we didn't return a vector of moves. Looks like we did. It's a problem with the concept, not with.
Can't the compiler detect that move and move t is the same type?
I don't think so. I mean, we could change it. I don't think it's because the problem is not with our game. It's with the concept itself. It says you cannot have constraints like this. Okay, let's do it differently. List. There has to be a move list. And this have to return. Oh, that's interesting. So let's see if it works. How about I leave it as it was and say that I don't know if it works. I don't know that if concept can do this, but it's worth trying. It has to be a constraint. So now say no. Okay, so let's do it the nice way. Something convertible to the list of moves. Oh, that. Okay, let's type that. So it didn't improve much. Maybe it's a problem of constness. Get the moves. You don't have to mutate. Yeah. And now I'm interested. It was a problem with const. Will it work back? Yeah. Maybe we need this one. So okay. No, but now it doesn't make sense to not use it. So now, rather than doing this if inside, we can use this function. So I'm not a big fan of almost always auto, so we can type it here. And then we say that for each move, no, it's not empty. It's not I anymore, it's M. Best move is and perhaps it will just work. Actually, can you see me anymore? Because I realized it's dark. Maybe I'll switch the lights on.
Yeah, a little bit better.
Okay. So it still works, but now we can see that we are extracting the index. In a game, in an abstract game, like maybe even more bizarre than chess, there may be no such thing as an index. Or move is not an index, so we shouldn't be seeing index here anymore. There should be a way. Well, why do we need it here? Actually, here we can turn everything into move. We don't have to return index from the game, but we can return a move. We'll do it. But here we can state in a more abstract term that we want to apply the move M to the state of the game. So this will be another part of our concept, that it should be possible to apply a move. So it has to be a mutable game. Apply a move. But how do we introduce the M here? One way to do it is to use another requires clause. Like we'll use one for, or let me write it down and then I'll show. We'll use one for the type types and the other one for the expressions. Actually, one would work here. Putting something here in the arguments of requires clause is also like a constraint that will be checked. But I suspect that this way I control the order in which I introduce constraint, and I suspect the error messages to be better. So I will first check for the types and then check for the functions in the interface. Okay, so there will be apply. And to apply it is to so I'm using a reference to const here. I'm using a value here, which is the same as L value. Maybe I'll make it say board index is if player is lost, then I want to put not there, otherwise I want to put a cross, and I need to swap the player. I think it just works. Now there is no braces here because I'm not interested in specifying the return value. It can return whatever it wants. That lucky. Reduce this. Because we didn't use it yet. This is why the file is so nice. And we just Of course, we could add another function here because we could put something that takes a state and a move and returns the next state. So these two lines would become one. Maybe for now we just ignore this. Next thing is we do not want to know that there is an index here. So we will be returning a move. So best move is now optional move. And here we are just assigning and apparently we're making a copy here, so our move has to be copyable and movable type. But maybe we will come here later. Let's make it regular. Now I'm actually expecting too much because I never care if this move is default constructible. I will never default construct it. So it's a dubious requirement. I follow the technique, not sure if it's a good one, that maybe someone else, when they will be implementing their algorithms, maybe it will be easier for them if those moves are default constructible. Maybe it's easier to write down an algorithm with default constructing objects. So this is one. This is another place where I use it. And now in the main function, I'm actually getting this move. And look here, I'm also taking this move only to apply it again. So I can apply it here. There's one more place where I apply it here. But it's a, no, I didn't really solve the problem because this one returns a move, but this one still returns an int. So I have to fix this one also. Move because it's called move here. Taking a shortcut here. And that's all fine. it's just int. It's okay. But here, when I return it, I need to change it into so this guy, which takes a string at some point here as an input and needs to convert it into move, he understands the game, that there is a array inside, that there is integers going on, and I can leave it this way because obtaining a move from a console is not part of my generic algorithm, so it doesn't have to be constrained by the console. Let's see if it still works. Doesn't work. It's not members. Yeah. It is no longer capital letters in the standard. Well, now it's more of the errors. Okay. Let's start with the first one. Unsatisfied constraints. So regular is not satisfied. Let's see if we can fix it easily. If you are saying, looks like it is default constructible. This isn't a good idea what I'm doing right now. I'm assigning some values 0. Take that back. What is it? Regular is not satisfactory. Why would that be? So let's take a step back. I accept. But can you tell me if this move that I'm seeing is regular, or if it is something else? Because regularity requires comparability. And I don't need to compare them, at least not now. So it's semi-regular. Now my game is a game. And everything compiles. Well, let me test if it still works the way it used to work before. Yeah, it looks like it works. Moving on. We arrived at the situation where the only things we are using is, okay, level is an integer, it will not change. Score, yeah, it will take that. Player. I guess the player, that means whose turn it is cannot be hidden from the algorithm, because this way the algorithm determines whether it looks for the maximum score or the minimum score. So there will have to be a way for this game concept to say whose turn it is. I think the only way place where we, or let's see where we use it, because there is a number of ways to do it. Either we provide a two-state enumeration, or we provide a true-false function that returns a Boolean value. Which one is more convenient? We can determine by looking at the functions that use it. I'm trying to figure out if we can. No, there is just one place that uses it. So it's possible to just provide a true-false function that returns whether it's yin or yang. So let's call it yin turn. It should work. It should return true or false. We cannot say it just like this. We can say it's convertible. And use it. Okay. Well, it worked. Is there anything left that is not part here? We are making a copy of a game. Again, we never needed to default construct because it comes as an argument to our function, but it needs to be copyable in order to perform some what if analysis. Here we'll not do, because this is the second time we encounter the same problem. Maybe we just require that it's copyable and movable. I mean, I think it is movable when it's copyable. Or not. Let's see. Copyable requires movable. Yeah. So it needs to be copyable, and the same applies to the game itself. Okay, we are applying a move. We are scoring, and for sure we will have to do something here. We're calling better. We'll have to inspect it later. Yeah, this is just assignment. This is just okay. So let's go here. Function score. Finished. We already have this. So level is just an int. It works. Static score, and so it comes to the static score, and the static score has to know it inspects the board. So here we arrive at the interesting problem, because the game, when we write the game, we say what the state is. It is, okay, this is this field, this is you win when you put 3 crosses in a row, it's clear. But to assess who has advantage in the game, because this function static score says who has a tactical advantage. If we cannot determine who will win ultimately, we have to stop at some point and determine who has the tactical advantage. And the tactical advantage is nothing really precise. Usually it's just our feeling. Like in chess, you say that the rook has 4 points, the knight has 3 points, but it's just approximation, almost like a random number. And it doesn't take into account the position and the other stuff. So it's just our assessment of the situation, and it is not really part of the rules of the game. In order to assess it, you have to know the game. You have to know that there is a board, that there is pieces, or that there is symbols, but the game doesn't have to know about it, which means that it is external to the algorithm, this approximation function, and it is external to the game itself. And we will reflect it in our algorithm with another concept. Like there will be it will be a, how can we call it? Assessment function. Here, yeah. And there is possible 2 different algorithms for approximating the state of the same game. One people can say it's if you have more pieces, you have more points. Another person can say if you have strategic areas in the board, you have advantage. So even for the same game, we can provide different algorithms of assessing who has tactical advantage. So we cannot say that the game has something like, because there is no one function that applies here. So it has to be a second template parameter to our algorithms and in our concept. If anyone can think of a better name, just say it. I would call it assessment. But actually, the only thing where it has the only thing we require that it's invocable. For invocable. invocable. That we can invoke f with the, okay. So it would be like, maybe we don't need a concept here. Maybe we just need, let's first pass it just without any constraint. Maybe let's do it in steps. Sorry. Okay. And we'll pass it our function f. Only two, why is it 4? Only two pass it down here. So our compute score then we just apply it here. And that's it. And we have to repeat it here. Yeah. And the name of the function is static score. We will have to, let's leave it like this for now. We'll probably not need it. Let's call it out. And at some point we're invoking the function. I don't know if it will work like this. No state. So and the second one is here. Let's see if it works. No, not really. Okay. 42. So the F is repeated. This will be easier. And so, where is it? 53. Pass it down. It works. Okay, so it works, but it's not constrained. In order to constrain it, we would have to say that what was the name? Invoke. Invocable with G. Let's say it worked. It's, I don't know if I should do it. Okay, let's do it decently. Invocable for, it means that here the concept has first what is invocable function and then the arguments. But in this location inside this template and angle brackets, I can skip the first argument. So I'm skipping f here and only provide subsequent arguments. And call the entire concept f, like here. Game takes one parameter, but I skipped it. I didn't provide it. works. So at this point, I get a more or less confidence that I am using the concept correctly. That is, I'm not using anything, no, not a single operation here that is not required by my concept game. But I may be wrong. So that code and I have made mistakes. So the next step is to make sure if I'm not using some ints that I'm not supposed to, because the template will not tell me. It will compile every instruction that I use inside as long as this concrete type provides, but not necessarily through the concept. Also, for now, I'm using ints because technically I could say that the score can be something abstract, like something that can be comparable, but not necessarily int, like big integers. But I skip it for now. Now I want to just check if I am only using the operations that are defined in the concept. And for this, I will introduce the concept archetype. I will provide a type that implements the concept and nothing more. So I'll do it here. Let's extract. And it will only provide the very minimum. By default, I get default constructor. I want to get rid of it. Don't require it, so I will not provide. The functions that I get by default from start is the copy and move constructor and assign and destructor. But those I actually require. I say that the type needs to be copyable. So it's good to leave them here. Maybe I could say it explicitly, but we are running out of time, so I will skip that part. There needs to be a move type inside. And this type I only require that it's copyable and nothing more. And of course, move has some special need to have something inside, like it represents part of the state of how the state changes. So it has to have some data, but I'm not interested in it other than game being able to apply this move. It doesn't matter what it has inside as long as the game knows how to apply it. So here I only say that default constructor I don't want. Delete. What else do I need to provide? Okay. I think there's something wrong here. Because never do I say that once I get this list here, let's go to the solver. I get the list of moves, and I need to be able to go begin and on it so that the iteration works. So it has to have a range interface. I could go and implement the range interface or require it here, but I think GCC does not support it yet. So again, maybe for the brevity of this talk, rather than requiring a move list, I will go back to saying that this thing is convertible to vector. So I will embed the vector in my console. It's not very nice, but I don't, just for the brevity of the talk, I don't want to go and specify that there is a begin is an iterator, and the like. So I'm not using it so far. So hopefully it still works. It didn't break anything. Well, I did break something. Still vector. Yeah. It should be the vector of moves, not move lists. The game works. And next thing in my archetype is we have move, game is copyable, finished. So there will be a function finished. It's very strange that they didn't make it a member function. So the only way I'm not now changing it into a member function is to show that the concept does not necessarily have to require member functions to exist, but also a free functions. But I can make it a friend. Spirit. I will probably need to implement it. So it doesn't matter what I return. It's just that it has a signature and that it links and compiles. What next? Possible moves. We return a vector. What next? Apply. Apply is easy because it returns nothing. Let's know what else do we have? Return that returns foo. Okay, and what else? nothing else. So, and we may provide, okay, the game finished at this point, so we should be able to assess that our archetype is actually a game. Now we are testing the test. The archetype is only to use to statically test our algorithm. And now we are testing if our test will work. It will. So the next thing is to check if our solver can be instantiated with, where's the solver? Let's copy. So that's right. Here is an important stuff. There is no way to construct game archetype because it can only be copied, but you need to copy from something. So there needs to be a constructor other than is copy or move, but we don't require any, and we don't provide it. So the way to overcome this is to just take it by reference. This function will never be executed, so we will not provide the argument, but it will be instantiated. Its body will have to work. So we'll pass it the archetype level like 1. We need to provide a function. So we need something, an archetype for a function taking a game. So let's again, not default constructed for my means. And taking game archetype. And return whatever. We'll take it here also. We'll provide it here. And the result needs to be convertible to archetypes move. Test. I think that's it. I try to instantiate. At this point, if my function solve uses anything else than this minimum implementation of game concept, I will get the compiler error. And I did. There's that for a mundane reason. I was not no. was not declared in the scope. Yeah, and what's the difference? Ah. What do we call?
It looks like you miss variable name.
Yeah. So let's P in order to avoid warnings. Just say that we are not interested in using this word. Yeah, so it compiles, and this way I prove that the algorithm solve does not use any other operation than those minimum here. There is no access to board in this algorithm, and I can apply it to anything that satisfies my concept. The next step would be to implement a different game. Well, to implement a different game and to check if it still works. You cannot really implement a different game in this short amount of time, but we can change this one. It used to be 3 by 3, and we can make it 4 by 4. Solver should work, so it should compile. Yeah. One adjustment that we have to make is to reduce the level, because now we are solving a bigger game, and if we use the search depth 10 move, it will not go to an end, it will hang forever, so we have to reduce it to something like 6. Things. Now it takes longer time because fine. Anyway, it works. So we achieve the level where the solver is now a generic algorithm. So we are able to provide the abstract constraints and only using those constraints to implement the entire algorithm. It's the first iteration, so we know it works to solve the noughts and crosses algorithm. We are not sure yet if we applied it to checkers for drafts or chess, if it would work. Maybe we forgot about something here, but this will be only become apparent when we have done the second iteration, when we have implemented another game compliant with this interface and check. Maybe it works and we are the master, or it doesn't, and we learn. We can refine the concept. We can see what our concept is missing and refine it. And maybe then it will be perfect, or maybe we'll make another iteration and another. And I think we'll break at this point. We are past 9 minutes time. If there is anything you want to comment on or ask, maybe it's the right time. And I think we'll stop here. I guess this means no questions or comments. We are past 10 p.m., so maybe it's time to go to sleep. I want to thank you for listening to this talk. I hope there was something interesting to take. There is a lot of mistakes and also a lot of looking at me solving problems, but maybe it reflects how working with concepts and generic algorithms works. Sometimes just looking, refining, understanding what you didn't get right, iterating. Okay, I think I will try to close. Thanks for attending this talk. I encourage you, if you have something to share, to contact us, and maybe you can run next episode of our meetup. And I hope we'll meet again next month. That would be in July. Thanks, and I'm closing the session.